Hello again, everyone. I am here yet again to talk to you, and this time it's about volcanoes and volcanic ashes. And we're going to be talking specifically about how volcanoes and climate interact and how we study that interaction in Antarctica. So the image you see behind me is not, in fact, a volcano from Antarctica, but it's a volcano that you might be a little bit familiar with. This is the Mount St. Helens eruption. So this happened near the city of Seattle, and it was felt all the way in Montana. So you could collect ash all the way into the Dakotas even, had you been there. So it's very characteristic, right? This volcano, big stratovolcano. It put millions of pounds of ash and debris into the air, and believe it or not, these kinds of volcanoes happen all over the world, and they happen because of the processes that go along with plate tectonics. So you see here the subduction zone that you might be familiar with. I know you've talked about plate tectonics. So a subduction zone is where an ocean plate goes underneath a continental plate, and this diagram is actually the ocean plate that goes under the state of Washington and is responsible for the magma that creates Mount St. Helens. So you can imagine this is underneath the surface of the Earth, underneath Seattle and the coast of Washington. And when that ocean plate goes down and goes underneath the continental plate, it starts to melt. And it does so because there's water in the plate, it gets warmer as you go into the Earth's crust, and so all of these things combine and they add up to a magma chamber. They add up to the processes that can make a magma chamber that form a volcano. So as this magma gets warmer and warmer, it moves to the surface of the Earth. I know I'm reviewing all this for you, but what's important is that the magma is unique to the area of each volcano. So it's unique to the conditions under which that volcano was made. So if I picked up a piece of Mount St. Helens ash, I could, without knowing it was Mount St. Helens ash, I could look at the chemistry and I could know that it came from Mount St. Helens. So let's go back to our volcano. If you can imagine that you're standing nearby to the volcano, you're standing perhaps a kilometer away, maybe 10 kilometers away in a safe area, that ash is going to start raining down and depositing. It's going to deposit on the surface of the Earth, and it deposits in a geologic layer. So if you've seen the other video I made, or maybe you've talked about stratigraphy or geologic layers, and if we look deep into the Earth's crust, if we look at the rocks and sediments on the surface of the Earth, we can see its history. So if this is an area near Mount St. Helens, we might be able to look back and see the ash. We would be able to look back and see the ash that fell because of Mount St. Helens. So if that ash fell in the early 1980s, we know that it had to fall on something. Well, everything that it fell on, if we're looking at it later, we know that everything it fell on had to be older than the ash itself. So if only there was a way to date that ash to know how old everything underneath it had to be. Well, convenient for us, the scientists have been able to use the chemistry of ash to date it. So we're going to talk about this when I visit, or perhaps we might talk about it, or you and Mrs. Thomas will talk about it later, but I know it gets covered in your class. It's called radiometric dating, and it's a kind of a confusing topic, but it's just important to know that we use the chemistry of the ash to date it, so we know exactly how old it is. So again, if I know that this gray band here is ash, and I say that ash was made in 1990, it fell in 1990 from a volcano, I know that everything below it had to be older. So we look at the Earth, or the distribution of volcanoes on Earth. We see the Ring of Fire here, which is a popular topic that gets covered in geology classes. Volcanoes occur all over the surface of the Earth, and not a lot of people know that there are also active volcanoes in Antarctica. So we think of it as a really cold and desolate place. But in fact, there are areas that are warm. The ground is warm in certain places because of these volcanoes. So even though it's cold there is still volcanic activity. And we see here a map of where these volcanoes are. So if I go to our field area, which is down in this part, these are the Transantarctic Mountains. And so this is where our research group has done work in the past. And a volcano explodes in the past, like it has many times in Antarctica's history. It explodes and it leaves a layer of ash. Here's a volcano. This is a volcano in Antarctica. You can see a little plume of steam coming off the top because it's pretty warm. So a volcano explodes and it deposits an ash somewhere, right? Well, this is one of the places where it deposited the ash. So this is an excavated pit in the McMurdo Dry Valleys. So that's here again. This is a mountain range. So we're in the McMurdo Dry Valleys, and we're looking at ash and dirt that have been deposited on top of what's actually ancient glacier ice. So we're quite interested in knowing how old this glacier ice is. Well, like I said, convenient for us, scientists have been able to use the chemistry of the ashes to date it. So if we know the ash fell on top of it, we know that the glacier had to be older than the ice, than the ash that fell on it. So if we date the ash, we know how old the glacier is. It turns out this glacier, is the oldest known glacier on Earth. It's about 8 million years old, this piece of ice, and we know that because of the ash chemistry. So the other really interesting part about volcanoes and how they interact with Earth's climate is that volcanoes not only erupt debris and ash, but they also release carbon dioxide and other gases into the atmosphere. So over time, the Earth has been able to manage its atmosphere naturally by inputting carbon dioxide and keeping it warm. And so then when plants and other organisms take that carbon dioxide out of the atmosphere, it gets replaced by volcanoes. Now, the amount of carbon dioxide that's introduced by volcanoes is very small compared to the amount that humans are putting into the atmosphere. But this is important because there are volcanoes on other planets and in other places in this universe that are no longer active, and because there hasn't been a replenishment of material. Plate tectonics has stopped, and when plate tectonics stops, it doesn't allow those volcanoes to erupt and to release gas into the atmosphere. So Mars, for example, doesn't have an atmosphere anymore, and part of that is because it got so cold that plate tectonics couldn't keep recycling things, and volcanoes, that magma never generated, so volcanoes went extinct, and there was no carbon dioxide or other gases introduced to the atmosphere. So how do we know about the volcanic input to the atmosphere in the past? Well, it comes back to this glacier here and this ice. We can look at the gas that is trapped inside the glacier, and we can look at the little bits of the ancient atmosphere that were trapped when that glacier was made. So we know how much carbon dioxide was in the atmosphere then. And we also think we have a pretty good idea about how much ice was in Antarctica when that atmosphere was trapped in the glacier. So if we know how much ice there was, and we know what the carbon dioxide in the atmosphere was like, the only missing part is what was the temperature. So we have now, using mathematical models, numerical models, and other pretty advanced concepts, we've been able to link the amount of carbon dioxide in the atmosphere with a temperature. So looking at this glacier and the gas inside of it, we know how warm it was and how much ice there was. And that's really important because as we look forward into the future, we're interested in knowing how much carbon dioxide we can put into the atmosphere as humans before we start seeing our ice sheets melt away, get too warm and collapse. So it all kind of comes back to volcanoes and their use in our research. And that is, if I'm recapping right now and recapping everything, we have volcanic ash that's deposited that we can date and we know the age of. And we're also interested in that volcanic input, the carbon dioxide, in the gas in the glacier that we're dating. So pretty interesting concepts. That's, like I said, it's a pretty short talk today. That's all I have for you. But we're getting ready for a big conference next week in New Orleans. And at that conference, I'm going to be interviewing many of the leading scientists in a lot of these different disciplines, and I'm interested in sharing their work with you. So I'll be making a video for you all about their work, and they're going to be sharing some of their recent findings in a broad range of fields. So you have that to look forward to. I'll be visiting you later in December or maybe early January while I'm in Montana over the holidays. And I look forward to seeing you all and maybe hearing some questions about volcanoes when I get there. So thanks.